All right. Can you see my screen? Probably not. Okay. So can you hear me all right? Okay. So we are basically arriving at the part of our course where we focus on the universe in large scale. So we start the course focusing on what's going on around us on planet Earth. So we see stars drifting about from the eastern sky all the way to the western sky, and then we learn this is caused by Earth rotation on its axis of rotation. And then we also realized um, that certain constellations are visible on few months of the year, but not all through the year. And the main reason is, in addition to rotation on its axis, Earth goes about a revolution, a yearly revolution around the sun. And and then later on we say, okay, so our planet Earth is not in the center of the universe. There are other components in our solar system. We have a sun, we have planets, we have moons, we have asteroids and comets. And then we studied a little bit of what we call planetology and what are the processes governing the evolution of our solar system. And then we arrive at the point in chapter 10 that we learn the tools that enable us to measure stars. Stars are far away, very far away. So if you take the closest star, which is Proxima Centauri, it's 4.3 light years away, which means if you take the fastest speed there is, and that's the speed of light in the vacuum, 300,000 kilometers per second, and if you manage, which we can't according to relativity, but if you manage to travel with the speed of light, it would take 4.3 years to arrive there. Our solar system, with all its dimension, is a quarter of a light year, just to give an impression and some idea about space, how empty it is and how large it is. Now, even the closest stars, in fact, all the stars we see, they are not, in fact, the end of the universe. In fact, all the stars we see and perceive, they are part of what we call the Milky Way galaxy. And now we are entering the realm of the universe in large scale. And then we learn that our solar system, is just one of the stars among 300 billions of other stars in what we call our galaxy, our Milky Way. And then this chapter is about measuring galaxies. In fact, we learn that our Milky Way galaxy is not alone in the universe. And then we are going to learn that galaxies, in fact, they group themselves in what we call clusters. And our Milky Way galaxies, this collection of 300 billion stars, in fact, belong to a local, what we call local group of galaxies, and Andromeda is part of it. So Milky Way and Andromeda are the two biggest galaxies in this local group, comprising of 3 or 4 dozens of galaxies, most of them small dwarf galaxies, and Andromeda and Milky Way being the biggest. And and is labeled by the astronomers because of the small number of galaxies as a poor cluster of galaxies. So our local group of galaxy, where Milky Way located, is a poor cluster of galaxies because there are not a lot. Now, rich clusters of galaxies are out there like Virgo, Coma, and they have thousands of galaxies. Just think about it, how populated this universe is. I mean, if you open your window effective. We don't have light pollution. So if you open your window and you look out there in the sky, you see all these nice, bright, little stars, twinkling out there. In fact, they are close to us, and they are huge stars. That's why we can see them. But they are relatively close. They are less than 3,000 light years away from us. 3,000 light years away from us. And our Milky Way galaxy has dimensions of not 3,000, but 100,000 light years, edge to edge. And our Milky Way galaxy is one among a 46 or so of other galaxies in these poor local clusters of galaxies. And I'm telling you, there are out there rich clusters of galaxies with thousands of members. But it doesn't stop there, because all these clusters of galaxies group themselves in what we call super clusters of galaxies. So these super clusters of galaxies are filaments with groups, with clusters of galaxies out there, and they kind of cover and surround voids with nearly empty space, and these voids happen to be expanding. So when we talk about the expansion of the universe, which is going to come next week, when we talk about the expansion of the universe, we are talking about these voids that are rising its volume, its growing size, and then we see all and we perceive all the other galaxies that are relatively far further away from us. We see all of them moving away from us as a result of this universal expansion of the universe caused by who knows what. I mean, it's still under investigation. So this chapter is about measuring galaxies. So we had one chapter that we learned how to measure stars using photometry and spectroscopy. So this chapter is about measuring galaxies. And galaxies are these large complex structures with hundreds of billions of stars. Now, um, first of all, a cosmological principle in science, principle are ideas, general ideas that govern uh, other ideas. So a principle you cannot prove. You assume it is up to the point that you can find some counter example that defies and breaks down the principle. Um, so the cosmological principle is one that says that the universe is homogeneous and isotropic. So what does it mean to be homogeneous? So it means that if you take the universe and take a scoop of it with several millions of light years in extent. So you take a little sample of the universe, and you can take this sample anywhere else. The universe will appear to be the same. So to be homogeneous means it's the same locally speaking. When you take an average, I mean, of course, the universe is not homogeneous in a small scale. Like our solar system is not homogeneous. You have the sun, and you have planets, and you have satellites, and they are not equally distributed in space, right? But if you take a large, a vast, enormous volume in space, it looks the same. The density, as we say, of galaxies seems to be the same. Now, isotropic is a different concept. It means that if you take nice, powerful telescopes and you look in any direction you want, you're going to see something that in average looks like the same. So you look east all the way to the end, to the furthest object you can, and you look west, opposite direction to the furthest distance you can, and what you see is a universe that looks the same no matter where you look. So these two principles are used to attempt to explain how the universe came about, and how and perhaps to predict how the universe in large scale will you evolve. So what galaxies are? So galaxies are complex systems that include several stars, not just several stars, but not. I mean, there are galaxies called dwarf. They are small in volume and population, and they have hundreds of thousands of stars. Just stop and think about it. I mean, our sun is just one star. So think about dwarf galaxies, small galaxies. There are hundreds of thousands of members part of it. But in general, galaxies like our spiral galaxy Milky Way, it has billions of stars, hundreds of billions of stars, just to give an idea how populated that is. But not only stars populate galaxies. In the region between stars, astronomers found what we call interstellar material. There is material in between the stars, and this material, as we studied before, especially in the chapter of star formation, this material is responsible for introduce features in the starlight as it moves towards us. And the type of galaxies out there are all types you want. But in general, most of the galaxies appear in this shape, and we call spiral galaxies. Why is spiral galaxies? Because they have spiral arms, as you can see in this picture. So this picture here in my right-hand side indicates three spiral galaxies, and you can see the spiral arms quite well. In the left-hand side, these other galaxies are seen almost edge on. So if these two galaxies were the same, and they are not, on the right-hand side, you are looking pole on from top down, and in the left-hand side, you're looking across the disk, the galactic disk. So, but galaxies appear out there in three basic shapes: spiral, ellipticals, oops, and irregular. So let's see the difference between those galaxies. So spiral galaxies, they first have spiral arms. Second important feature of spiral galaxies is that they have a cold gas, with 1% of that cold gas being filled by dust. So what this indicates that the temperature of this interstellar material is relatively low, which means spiral galaxies, because it has gas and because the gas temperature is low, it favors star formation. So look at this galaxy over here, the second in the middle, in the left-hand side. If you look across the edge of it, it has a dark dust lane going across. And this dark dust lane is the result of dust that is retrieving light from the stars that happen to be populating this bright area that we call bright volume that we call the bulge. You can see also this dust lane in the first picture on top, and you can see dust lane in all spiral galaxies. So a telltale of spiral galaxies is one that has these dust lanes absorbing and retrieving lights from stars that happen to be in the bulge. Now, elliptical galaxies are somewhat different. Elliptical galaxies, let me see if I have pictures of elliptical galaxies. So elliptical galaxies, this is a good example. So elliptical galaxies are one that appears in an elliptical shape. Let's see if I can get something. So as an elliptical shape, they have this oval shape, and you don't see evidence of dust at all. Like in the spiral galaxies, See, you have dust, dark dust lane going across. In elliptical galaxies, where is it? In elliptical galaxies, you don't see those. See that? Oops. There you go. In elliptical galaxies, you don't see that. Like this is a spiral galaxy. You can see the dust lane in there. This is elliptical galaxy. You don't. So spiral galaxies are classified by the ratio of the bulge, this bright globular and luminous center part, the size of it in comparison with the size of the spiral disk. For instance, look at this bulge, this bright bulge. See, this bulge that I'm showing right here, and the disk itself. So the bulge is smaller in volume or in dimension than the spiral disk itself, but you can see spiral galaxies in which the bulge itself seems to have a volume or a dimension that is comparable with the galactic disk itself. So spiral galaxies, spiral galaxies are classified as SA, SB, and SC galaxy. And the difference between SA, SB, and SC has to do with the ratio between the size of the bulge and the size of the spiral arms. Our galaxy is an SC galaxy. Now, some spiral galaxies, they show through their central bulge, they show a bright region that appears to be a bar. Let me see if I can show it here. Right there. See, this galaxy over here has a bar-like structure that crosses the bulge. So these galaxies are classified as SB, B for bar, SB spiral B A, or SBC, SB A, B, and C. So these SBA, SBB, and SBC are spiral barred galaxies, and again they are classified by the relative size of the bulge when you compare with the size of the disk itself. Now, what this slide is showing is the global motion of the stars that happen to populate either the disk or the bulge. A star and the bulge, they go in any direction. They don't go in a global way, like a herd of ships that move in the same direction, right? Or a herd of antelopes that goes in the same direction. So the stars in the bulge, they go in any direction they want, and that's what these vectors here, these arrows, indicate. Whereas the stars in the spiral arms, they tend to follow a pattern. They go around the galactic center, obeying some rule in some global direction. In fact, our solar system is about 2/3 of the way in the spiral arms, and the solar system takes 200 and so million years to complete one turn around the galactic center, but it goes along with other stars and towards the same direction. And the reason why the spiral galactic disk, you have stars that migrate and revolve around the galactic center in the same direction, is because, as well as we learn in our solar system, where the circumstellar disk out of which planets and satellites and the asteroids were formed, they all seem to be orbiting the sun in the same direction because they all came from the same disk. So in spiral galaxies, the stars in the spiral arms, they all go in the same direction because they were formed out of the same a circumgalactic disk that revolves around the bulge, the galactic bulge. That's another example of a spiral galaxy. Is why this is a spiral galaxy, because there is a dark dust lane you can see clearly in this picture, and more so in here. So gas and dust are concentrated along the spiral arms. This is where the stars form. Now, why do we see spiral arms in spiral galaxies? Why do we see the arms? Well, arms are the result of what astronomers call density waves. These spiral arms are formed as a result of gravitational tidal interaction of our galaxies with nearby dwarf galaxies. And this interaction provides enough energy to concentrate gas in certain regions where we call spiral arms. And as a result of this concentrated gas, stars are formed. So once stars are formed, it forms a small population of O-B stars, and as we studied previously, O and B stars are hot and luminous stars responsible for producing a large fraction of ultraviolet radiation in a galaxy, and this ultraviolet radiation these OB stars produce light up the spiral arms, and then we see them. So spiral arms are not regions where stars happen to be populating. So it so happened that spiral arms, we see them and not the region in between spiral arms, because in the region in between spiral arms, there are no OB stars. They are gone. Once OB stars are formed, in few million years they are gone. They evolve quickly, as we studied in previous chapter. So but the number, the percentage of stars in between the spiral arms and in the spiral arms itself, the number of stars is about the same. Although in the region in between stars, there are no OB stars, okay, because they are gone. They are. So this is an explanation why these spiral arms are not the result of galaxy rotation alone. So spiral arms are the result of density waves, and probably they are triggered by interaction with the nearby galaxies, dwarf galaxies in our local group. Now there is an important point in this chapter, and that is the introduction of a concept we call dark matter. So dark matter is, we don't know what it is. One of the properties of dark matter we know is that it's responsible for attracting things, responsible for providing a gravitational tug on things, but is a type of material that do not absorb light and do not interact with light. Why is that? Because we don't see it, and we don't see it interacting with light from galaxies that are further away, that happen to pass and move towards our telescopes. So how do we know dark matter exists? This was suggested early in the 19th century, um, as astronomers observed clusters of galaxies. So observing clusters of galaxies, what you really see is galaxies, the dynamics of galaxies in clusters, right? By dynamics, I mean when you observe using spectroscopy groups of galaxies that happen to be part of a cluster, using Doppler effect, you can estimate and predict the dynamics of that system, which means you can predict in which direction galaxies move and how fast they move. Now, here's the catch. Observing this group of galaxies very far away, called of high density, of a high density number of galaxies, it was found the galaxies themselves, they seem to be held in place by some material that astronomers were not seeing. I mean, they are going faster, they are moving with very high speed, but they were not being flung away from the cluster. Imagine a situation in which gravitational interaction would provide planets in our solar system or asteroids, just to give a nice, simpler example. So the interaction of planets or planets with satellite might give small objects with less material, might give them the ability of being flung away from our solar system. What it's like this um, uh, a three-body interaction. The third one is pretty much casted away. So some gravitational energy, potential energy, is given to a third body, and this body just go away. That's how we saw before the Oort cloud of comets surrounding our solar system might have been formed in the very early stages of our solar system. It's just a three-body interaction. Now, observing this group, these density clusters, these high density clusters of galaxies, they were moving very fast, but they were not being casted away. They were still held in place by some gravitational force. And then Zweig, the astronomer, suggested that there was some unseen material which was labeled as dark matter that kept the galaxies in place. More recently, it was found that stars in our galaxy and in galaxies nearby, they also tend to obey the same law. So if we apply Kepler's law, which means the laws that we learn out of Newton's gravitational force, to stars that happen to be orbiting the galactic center at regions further away from where we are, we would predict these stars as you move away. So in this graphic, the top graphic, um, uh, it show in the y-axis um, um, no, I want to show this one here. In the just by showing uh, the but just by measuring the rotational velocity of stars further away, you would expect the density or the velocity to grow as you move away from the galactic center to a point the orbital velocity diminish as a result of Kepler's law. Like planets further out from the sun, they orbit the sun at a speed that is less than the speed of planets nearby, like Mercury and Venus. So as you go to Saturn and Uranus, they move with a speed that's much less than the speed of Mercury. That is pretty much close. This is the so-called Kepler's law applied to planets. And when you apply to stars in our galaxy, you would expect a curve like that. Now, what you really observe is the last figure over here. See, the decay of velocity doesn't happen. It flats out, as if our galaxy were surrounded by a material we don't know what it is, and astronomers call dark matter, and is about 90% or more of the material required to explain the dynamics of our galaxy. So guess what? So our universe, the universe of visible objects comprising of galaxies and stars, 90% or more of that universe, we don't know what it is. We don't observe. We don't see it. We know it's there because it causes effects in stars we can observe. So we know indirectly they are there. This dark matter exists because of its effect, but we don't know what it is. But in our lifetime, we might be able to get candidates being proved, solid candidates for dark matter. There you go. So this is the observed rotational curve of stars. So as you go away from our solar system that happen to be somewhere, this in blue is the mass of dark matter required to explain what is observed. I think I went back for some reason. So machos and WIMPs are projects designed to detect dark matter and try to explain what they are. Machos and WIMPs stands for weakly interactive massive particles, and these WIMPs might be they are the strongest candidates so far, and they are particles. They don't interact heavily with particles as we know, like protons, neutrons, and electrons, but they can be created and they can be analyzed in heavy colliders like the Hadron Collider. And perhaps in our lifetime, we might be able to prove these WIMPs, these particles exist. And machos are massive compact halo objects. So machos are objects that happen to be in the galactic halo. They don't interact with matter so much because they are compact, but we are able to observe the effect of their presence by the bending of the light as it passes them. But the amount of machos that have been detected after several surveys done is not enough to explain dark matter. So dark matter supposedly now is primarily its primarily candidate is pretty much WIMPs. Now, the less important aspect of this chapter is that galaxies, like our Milky Way galaxy, they show and they present what is called a supermassive black hole in their very core. So why is that? Why the center part of the galaxy show the presence of black hole? So when galaxies were formed about 10 or more billion years ago, the material that happened to be attracted to its center of mass, the material attracted to the center of mass formed the very first generation of stars, and out of which black holes start to be formed, primarily in the core and the center part of galaxies. And since that region was populated with gas, this gas ended up being fall and ended up being fed to these black holes, and 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 that's how these black holes in the galactic center, that's the hypothesis that pretty much suggests their existence. Not only that, they are, I mean, we don't see black holes because the light of a black hole never escape, or the energy does not escape, or information does not escape a black hole. But we can see the effect of material falling onto the hole, and as it falls, it emits radiation, and we can predict not only its size, its volume, but also its mass. And and then now what? Well, you take your telescope, and this is a project done by Hubble. You take your telescope and you point in any direction, you find galaxies beyond certain distance, they tend to be flying away from us in a way that the further the galaxy is, the fastest it seems to be moving away. So you could interpret the data as if we were in the center of the universe that happened to be expanding, that happened to be flying away from us. But the conclusion doesn't hold, and the best interpretation of data we have is that those voids that I mentioned in the beginning of the lecture, these voids are expanding its volume. And as a result of which, no matter which direction we look, we see these galaxies pretty much flying away from us as a result of this universal expansion. This is the so-called Doppler the Hubble flow is the Hubble flow, and astronomers can easily measure that using spectroscopy. Okay, so those are the main topics. This example here is one of the best I know that helps to visualize expansion. So you have a string with uh, with clips attached to it, and then you give expansion in distance. Imagine that is an elastic, right? And then you expand this elastic, you stretch the elastic in certain amount of time, and when you do your calculations, you realize that no matter where you are going to see all the other paper clips moving away from you if you were one paper clip in such a way that the farthest it is from you, the fastest it seems to be moving away, which indicates um, this expansion or this receding velocity of galaxies is not the result of having them flying through space away from us, but space itself is the entity that expands. And as a result of the expansion, it takes galaxies along with it, and that's how we see them kind of flying away from us. And those are the main topics of this chapter 14. And I would like to remind you we are pretty much getting close to the end of our semester. We have 3 more weeks of class, and the final exam after we complete this exam number 3 next week. We have a makeup exam that I will open the week before final, and then we have a final that is comprehensive, but it's not online. You have to go to Evergreen with an identification showing who you are, and then you can do your exam. Ok, doc.
For the final, it's on December 17th.
Amanda, let me stop taping so we can talk. Okay, just a second.